Hey y'all, welcome back to another round of engineering. And yeah, I apologize. It came to me that I've actually skipped over a small little piece that's important for the Thevenin resistance. And so I'm just doing a quick video about that, and we'll call it good for that. So the Thevenin circuits, there is a piece that I skipped over, and you've probably noticed it already working on your homework. Now, the upshot with the Thevenin circuit, or the Norton circuit if you prefer to use current sources, so I get RTH, I've got a VTH here, is that it allows us to simplify any linear circuit as simply the potential supply and an associated resistance. And, we've worked through how to get the Thevenin resistance. You've got a couple of different ways. One way is deactivate sources, and I should say the independent sources, and find REQ, the equivalent resistance. Or a second way is to find the potential difference for the open circuit. In other words, remove the load, measure the potential difference, and then find the short circuit current. Drop a wire between the terminals and find the current through the wire. So that's how we get that guy. What I have failed to mention, aside from the utility of simplifying the circuit, is the advantage when we're thinking about the power delivered to the load. So I thought, okay, brief video on how to get that power. So imagine for a second that we have the Thevenin circuit and the load RL established. And the question is, what is the power that's delivered to the load? Number one. And second of all, what value of the load results in the maximum power being transferred to the load? So the first question, what's the power experienced by the load? Well, we could write that as I squared R. There we go. And in particular, we would use the current flowing through the load and the resistance of the load. Now, you probably already know what's the current flowing through the load in terms of our variables. Yeah, we've got two resistors in series. So we have V Thevenin divided by our two resistors in series, and we take the summation. Okay. And we square it. So there is the general expression for the power being absorbed by our load. Now the next question, what value of RL results in the load power being maximized? And perhaps instead of saying maximized, maybe I should say reaches an extreme value. Okay? And here's where we have to put our calculus hat back on. Okay? How do we find the extreme value of a function? Yeah, we take the derivative and we set the derivative equal to 0. So what do we have here? Max equals this rigmarole. And what we want to do is we want to take the derivative with respect to our variable and set it equal to 0. That will tell us the maximum value. So go ahead, run it. You got it? Good, 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 good. So let's go ahead. So what we have here, DDRL, and I'm going to write this as RL V squared, and that's the Thevenin resistance. And then I'm going to write it as RL plus R Thevenin squared, and negative squared equals 0. I just do it that way because, I mean, you could do the quotient rule, low d high minus high d low over the square of what's below. Okay? I prefer to do the product. So we have the derivative with respect to RL. So we end up with the Thevenin voltage squared times RL plus R Thevenin. And we have the -2 there. Then we have added to that RL V squared Thevenin. And then we take the derivative of the other term, RL plus RTH to the -3rd, right? We move the exponent down, lower it by 1. And now we see, oh goody goody, we have some cancellation here. Notice that each term has that Thevenin potential, so we can cross those out, right? There's a 0 on the other side. We also, each term has this R plus R Thevenin squared, or so to say, to the -2. So I can cancel this guy with 2 of those, so I still have a -1 here. And so I can rewrite this as 1 minus 2, and now I'll put it back in fractions just so that we can see it. 2RL, RL plus RTH. Almost done. If I want to get rid of that fraction, I have RL plus RTH minus 2RL equals 0. And oh goody goody, this cancels that. Oh, excuse me. Erased the wrong one there. Got overzealous. There we are. And so what we end up with at the end of the day is that our load resistor equals Thevenin, the Thevenin resistor. In other words, in order to have the maximum power transfer from the circuit to the load must be of the value of the Thevenin resistance. Pretty cool, huh? Also, while we're at it, okay, if RL equals RTH, okay, how much of the total power produced by the Thevenin source actually goes to the load? Yeah, hopefully you see it, right? If the Thevenin resistance and the load resistance are the same, then half the power has to go to the load and the other half goes to the Thevenin resistor. They're the same value, so yeah. So exactly half. Okay. So I apologize. I completely missed over that. I skipped over it and I thought, oh yeah, I should just do a short video just to remind you or to show you that little piece that was highlighted in the book. Hey, thanks for your attention. I'll see you next time for Op Amps.